Okay, so it's a great pleasure for me to introduce the next speaker, friend and co-author of mine, Dmitri from Swansea University, and he's going to talk about spatial temporal correlations in a class of interacting particle systems. Dmitri.
Thank you very much for the kind introduction, and also many thanks to the organizers for the invitation. And it's a great pleasure and honor to be here, and also many thanks for not blaming me and another participant from the UK for these rains here in Lisbon. I appreciate it. It's quite unusual, but fortunately it started not exactly this hour. This us. Right. So my talk today has a bit probably unusual reference for this conference because it's based on a joint paper in a quite applied journal in a Royal Society interface together with my colleagues from Finland, Otso, Ovaskainen and Panu, Somervuo. And actually the talk will be based, of course, about a method, and this method was mathematically proved and justified in this supporting information to that paper, which was apparently, the supporting information was apparently quite long. So what is it about? Spatial-temporal correlations. So I will speak about I'm working in continuous systems. So we consider, say, at moment of time t, we consider finite countable set of particles. They belong in, they lie in certain, in general, locally compact Polish space. The basic example is RD. But another important example to have in mind is this RD times some, say, finite set of types, marks, traits, spins, whatever terminology you prefer. So each point may have not only position characteristic, but also type characteristic. So for countable gamma t, which we call, of course, configurations, we assume that in any compact lambda in X, there is only finite number of points, also called locally finite configurations. Gamma capital is a set of all locally finite configurations. We can study different mathematical structure in this space, in particular sigma algebra, the smaller sigma algebra generated by all mappings from configuration to the number of points in any compact. And also we fix some non-atomic radon measure sigma on X in case if we have types non-atomic with respect to positions, of course. So which kind of processes we in principle consider? We consider general jump type process on gamma, so that after infinitesimally small change of time, instead of configuration gamma t, they have gamma t plus delta t. So what may happen, some group of particles may disappear from configuration and another group of particles may appear in the configuration. Both groups are supposed to be finite. So this covers, I believe, most of cases which were considered about all this discrete type evolution. So without diffusion, I mean. If, for example, omega is empty, this would correspond to pure death. So just group of particles disappear. If xi is empty, this would correspond to pure birth, new group of particles appear. If they have equal number of points, this would correspond, for example, to the jump. So that just group of particles change their positions. Or if they speak about, in this extended space, about position times types, they may remain the same position, but just change types, which would have analog in lattice systems about spin flip models, right? So then just the spin is changed. And also if omega and psi have different number of points, this would, let's say, cover at least the ideas I will present would cover the case. Then they have different coagulation fragmentation, splitting and merging. So some instead of 3 particles appear 5 particles and so on. Of course, the rate of so this random event happened with certain rate. There's a certain function which depends, of course, on these groups which appeared, disappeared, appeared, and also on the rest of configuration. This would give the interaction into the system, so this is some non-negative rate. The formal Markov generator of this process should satisfy the following relation. So we consider some observable for any function f from proper good class. We consider observable, calculate on the configuration, take average, and then mathematical expectation, and then the differentiate in T, and then here should be the Markov generator. Of course, if this Markov generator exists in certain sense. So the types of Markov generators we consider here are the following. So, as I said, any finite number of points from 0 to certain m minus may disappear from configuration. Another random number of points may appear and they are distributed somewhere in the space X. All right, so the rate of distribution is given by this function C, and here we have measure on these points, new points of the configuration, and here they have this elementary Markov difference between observable at a new point minus observable at the initial point. So this is formal form of the Markov generator we consider. So I will show, of course, some more simple examples. So the first order special correlation function, this non-negative function of one variable, it should satisfy the following relation. So this is a standard definition. If you have expectation of the additive function, then this any, say, non-negative kernel G1, then it should be exactly this integral of the first order correlation function. In particular, if we take expectation of the number of points in a bounded region, in a compact region, this is a random number, so this expectation would be given through the integral of this first order correlation function over this region, this measured sigma, which apparently also may include types and so on. Lambda also may be on these extended spaces. Similarly, second order correlation function can be defined using this identity. So we take any non-negative function of two variables, symmetric, and then we consider some overall pairs, and then the average, and then it must be the integral of this function, this weight. Since we will have a lot of upper indexes, I will not write here any index characterizing the order of the correlation function, but I will always write the argument, so from this it will be clear which order we consider here. And again, in particular, if we consider now two random numbers, so two regions, lambda 1 and lambda 2, and consider number of points in one region and another, then the expectation of the product will be given through the second order correlation function and also first order correlation function on the intersection. In particular, of course, from this formula, if the regions are disjoint, then it would be just second order correlation function. And also just to finish this, the well-known somehow classical things, we can also consider covariance. So in the standard understanding, so we have two random numbers, we consider covariance between them, two random variables, we consider covariance between them. This would be given through the second order cumulant, which is nothing but the second order correlation function minus product of first order correlation function. So these are the, of course, we can also define higher order correlation functions, and this is for this special thing, it's very important because for typical models, if you write down the differential equations for, say, first order correlation function, it will include second and higher order correlation functions. So we have hierarchicals, and if you write down the equation for second, it will be include higher order. So similarly, like we have, for example, in Hamiltonian dynamics and in many other dynamics, so we have a hierarchy of equations. However, here we consider it these two random quantities, number of points in lambda 1, number of points in lambda 2, is expectation or covariance. We consider it at the same moment of time. And in principle, it's a very natural equation and important, in particular for applications, but also just from general mathematical point of view, how we can study the correlation between random number of points at different moments of time, at different regions. So how the situation now and here correlate the situation there in future. All right, and in principle, so such type of formulas, it may be kind of our wish. So we want to consider, for example, the expectation of the product of these two random numbers. And we want to know, can we write down here a function which depends on t, which depends on delta t? Of course, here would be some comma, so some in some non-trivial way. By analogy, this is the previous formulas. So in principle, even mathematically speaking, it's unclear. So here it's possible to show that here would be some measure, but there's this measure, like joint distribution, but this measure has a density. But more importantly, practically, probably how in principle to study this quantity. And up to my knowledge, there are not any somehow kind of general theory. So theoretically, if we have what sometimes it's called random field, so then you consider kind of flow in space and time, then probably taking proper average simultaneously in space and time, you would get this quantity. The problem is that typically for all non-trivial models, you do not have that random field, unless, for example, this is kind of chaotic behavior, like Poisson measure in space and time simultaneously, then it can be done, but this is like a very simple example. So what shall we do in this, even to answer on this question about the second order correlation but in space and time? So the idea which was proposed in this paper was the following. We are going to introduce at some time t an auxiliary dynamics. So we're going to introduce at this time t, which will be the starting time for us, three types of particles. So we will have the global time of our system. So, and they want to measure the correlation between moments of time t and the moments of time delta t plus delta t in the global time. And they will have also local time on this auxiliary system. So delta t here, just to mention here, delta doesn't mean small. So delta is just the time lag. So in principle, it may be big. So at initial moment of time, at time t, this delta t is 0. And at this time t plus delta t, the local time of this system will be just positive number delta t. So what are these particles? So gamma delta t O stands for original, contains all particles of the considered system which were present in the system at time t. There's the same types. So, and in particular, initially in the local time, this was exactly that configuration which was present in time t. And they did not change their positions nor types within the whole time interval from t till t plus delta t. So they still present in the same positions with the same time types at this final moment of time of the considered interval. Next, we consider gamma delta t plus. These are all particles of the considered systems which appeared within this time interval from t till t plus delta t. So they didn't present initially, but they appear in some way. Either they were born, for example, or some particle changed position, or some particle changed type, and then this new position or new position together this type will be element of this new configuration. So these are all particles which appear on this interval. And also what is very important, they're still present at the time t plus delta t, because we have like a measure correlation between now and future, and they somehow interested only in those which appeared in between and still present at the edge. And finally, so plus stands for new somehow, and finally gamma delta t minus, this contains all particles of the considered system which were present initially, but do not present anymore. So either this particle disappeared, or this particle changed position, or changed type. So initially they did not exist, because initially all particles they are present. But these are, so informally we call them ghost particles. So they just show that at this point, initially was a particle of certain type, right? And it's not anymore. So why do we need these three types? Because now, yeah, and of course, just to mention that if they have additional several types of particles, then they introduce this auxiliary system for each of them. So if they have n types, then auxiliary system will be 3n types, right? So what is the, yeah, so before I will explain about what we can get from this, just to mention that the dynamics of original particles and plus particles is governed by the rate inherited from the dynamics of gamma t. So of the dynamics we consider, I will show examples. Minus particles, so they do not evolve by themselves, they just appear from the current original particles. And somehow all this was done because of the possibility to write down the configuration at time t as the union, so as a set, they may consider this as a union of the configuration of original particle at time delta t, so those who were originally and still are at time delta t, union those who were originally but not anymore at time delta t. Right? So if they combine them, we exactly reconstruct the picture of the original system. Whereas if we consider these original particles, this the union of a new particles, then we will get exactly the situation of the system at time t plus delta t. Because at time t plus delta t, there will be only the original citizens and the newcomers. And I remind you that these newcomers are those who did not disappear in between. So they came and they remain until the time delta t. And of course, if they have this, so, okay, let's first consider a few examples. For example, we consider the, say, part of the generator, there just one particle disappear. So it's just the pure death, any particle will disappear this rate. So then this would correspond to the following generator on this auxiliary dynamics. So what will be? Original particle may disappear, but then the ghost particle appear at the same position, right? So we need to somehow record that here was a particle, right? But label of this particle will be now minus. The rate, and this is the crucial, the rate of this event will depend, it will be the same function d, calculated at the union at original and new particles, because all particles which are in the system are influence, we need to take into account all interaction, are still influence the system. So during this time interval, all these particles interact, and because of this, they need to be reflected here. But also, it may happen that this particle which disappeared was a new particle. And in this case, of course, it will be just this, because as I mentioned, we do not care much, we do not need to count at the end those particles which appear and then disappear. But we need to take them into account at the generator, because again, during this time interval, they influence. And because of this, they are present here in the generator. Similarly, if we have, say, simple bursts, so a particle may appear elsewhere, one particle may appear elsewhere in space, this rate, then it would be a very simple operator, because now it's just a new particle appears. And again, the rate should take into account all original new particles which are present in the system at that moment of time. And if we have, for example, jump, so a particle, any particle from configuration jump from x to y, then the certain rate, then the corresponding, again, we will have quite long operator, because particle jumps, it means that it disappears from the group of original particles, but immediately it becomes, like, relabel it as a ghost particle, but also this rate, new particle appeared at the position y. This happened if the original particle jump. If new particle jump, it's just the kind of the same operator as it was here. Again, because we do not need to relabel once again this new particle. And again, the rates depend on both original. So I remind you that we have these inequalities, these equalities. Because of this, of course, we easily can calculate the densities, right? So we just need to add up density of original and minus, original and plus. But more importantly, we can just substitute these equalities here into the object we are going to calculate. And then just the quite elementary calculation, we can get the following formula. So what is written here? So what I actually did? We reduced the problem of finding the spatial-temporal pair correlation to the problem of finding, or studying, better to say, spatial correlations of these auxiliary dynamics of this extended dynamics. So we have now more types, but we can work only these spatial correlations. These are temporal components. And these objects are somehow can be studied now. We have, of course, initial conditions, which shows that initially original particle just follow the same evolution as the main system, whereas all combinations between original and new and so on are zeros, because just originally new particles didn't exist and ghost particles didn't. Oh, similar we can do for the covariance, and we have here the cumulant. Again, cumulant has the similar combination of the cumulants. So, a few examples where it works and how it works. First, this example, quite rare example, is this business about the exactly solvable but still non-trivial model, so-called contact model. It's not very much similar to the contact model in discrete case, let me say. So this is the model, then any particle may die this constant rate, and any particle may produce an offspring elsewhere in RD, this some kernel A. So this model apparently was first introduced by Darrett in '79, then considered by Kondratyev, Skorokhod, and then Kondratyev, Kutovy, and Pirogov. And here it's possible to calculate very simple the density of the original particles. It's possible to get density of the main system. Everything is explicitly solvable. And moreover, it's possible to get the differential equation for this spatio-temporal, say, cumulant, right? It's just easy to write down in terms of cumulants. This is linear, non-homogeneous differential equation, non-local. Of course, it can be solved explicitly. And what is important, one interesting example of the application of this method. So here in this model, in the so-called critical case, then an average number of appears, in average the rate of appearing is equal to the rate of death under some conditions, and in the space homogeneous case, then the initial density is a constant in space. There exists a limiting distribution. There exists the stationary distribution. So in the sense that when t tends to infinity, everything converges to the to certain correlation functions of all orders have limit, and moreover, this limit has a measure corresponding to this system of correlation functions. So what we can do now here, we can consider the following quantity. We can take this spatio-temporal second-order correlation cumulant, say. This hat means it's Fourier transform, and we can pass t to infinity. So for a second, it sounds a bit strange because they have like time t plus delta t. If we pass t to infinity, then both will be at infinity. But the meaning that we had two moments of time, and they have the time lag delta t between them, and there's no correlation between them. So what we are going now, we look what would happen if this time lag would be shift to infinity. So what we are looking, we have stationary distributions. What does it mean? It means that if you have evolution of particles, particles continue to evolve, but the distribution of the particles remain the same, namely according to that theorem. But of course, if you take pattern at this stationary regime at one moment of time and then at another moment of time, they will correlate, they will be different patterns, just the same distribution. And this formula shows how we can measure the correlation between these two patterns. That again seems to be quite difficult to do in other ways. Another possibility here to show then if instead we send time lag to infinity, then it would be zero. Oh, this is kind of expected results, meaning that if we have now and we have in an infinite future, then the correlation should be negligible, right? So this is so-called time independence, right? Okay, but this was a model where everything can be calculated. Now consider another model, so this kind of modification of the previous one, but now we have density-dependent death. So we have that particles die not only this constant rate, but also because of neighbors. Say these models what initially appeared in papers of mathematical ecologies, because these describe then say plants compete for resources, and because of this, plant may die if there are around a lot of other plants. Thanks. Yeah. So in this model, of course, we have hierarchy. So first order correlation function depends on second, second depends on third, and so on. So, and if we want to get something practically, numerically, and so on, we need, one way is to introduce the, say, mean field approach, the certain scaling. One of the possible scaling, we consider such CATS type kernels, so which have the same integral, and then they consider the initial condition of the following form. So the first order correlation function is certain Q naught calculated of epsilon x plus something small. Second order correlation function is a product of this. And here it's possible to show that there is chaos propagation of chaos property. So if we consider at moment of time t, they will also satisfy the same property. And the Qt satisfy the analog of the kinetic equation, non-local equation. So this was derived for integrable functions by Fourier and Méliard, and for bounded function in our papers. And the equation itself was studied also in series of papers. This my co-authors probably was about 8 papers, because it has a lot of properties. Of course, I do not have time to mention them. So what is possible to do here using this approach? Not much directly, first, because if you just apply this propagation of chaos in the mean field, then of course the second order correlation would be just so small. So what we need the next term of the expansion in this small parameter of the scaling. And for this we have also a method. So it was first proposed by biologists a bit informally, and then it was justified in our paper in theoretical ecology, and then it was also very much generalized in our paper in Nature Communications, because also it was provided with some computer framework how to calculate all results here. So I do not have much time to mention to go to detail. And actually, I gave a talk last year about this on this conference, but it was online. So this about how to get the next terms of the expansion for, say, first and second order cumulants. So it's possible to show that this next term of the expansion, these two functions would satisfy the closed system of linear differential equations. These the coefficients dependent on this solution of non-linear equation. And then it's possible to rewrite everything for that first term of the expansion of the second order cumulant, get answers, and then to do the same for all these auxiliary systems. So, and from this, we can get explicit expression for the leading term in the expansion for this spatial temporal pair correlation or covariance. And also under certain condition, moreover, again, it's possible to study what would happen if time tends to infinity. So what would happen in the stationary regime, and also just to mention that here it appears to be very well satisfied this computer simulation. So if you now run computer simulation for this model and calculate, because in computer simulation the calculation of the spatial temporal correlation is a simple exercise for for a student, right? You just take one pattern, take another pattern, and measure correlation. But it appeared that the computer simulations corresponds very well to the mathematical prediction, and it was also generalized for much more sophisticated so-called host-parasite model. Then we have host and parasites. I will not go to details about this operator. I will just probably finish, because here there are very, very long formulas, but apparently these formulas gave, again, very good predictions. So you may study how presence of host here correlates this presence of parasites or host there in future, and this work well even in, if you consider like you have now space component, time component, and so here you can see the mathematical prediction. Here you can see the results of simulations, and again, they matched very well to good order of exactness. Right, so I think my time is over. Thank you very much for your attention.
Thank you very much, Dima, for this nice talk. Are there any questions, remarks? I have one, Dima. Under which condition one can assure the existence of the spatial temporal, the correlation functions? Corresponding correlation measures, we know quite surely that you can assure the existence. But what about the corresponding correlation functions?
So there are somehow two answers on this question. The first answer is that as soon as you know that the correlation, the special correlation function exists, you know this for special temporal correlation. So this doesn't need to be a problem. But in principle, of course, what it's possible to do is to, okay, well, so you have this auxiliary dynamics, say three-component auxiliary dynamics, and you need to show that for this auxiliary dynamics you also have evolution, right? And you may consider those correlation functions.
So it's slide number 19, as far as remembering. After getting this decomposition here?
Yeah, so again, if you want to know about these correlation functions, then you need to look, for example, let's again go a bit back. Quite back. Sorry, I used the wrong direction now, I understood, because it's a bit not counterintuitive for me. So you have this generator on this extended dynamic, yeah, like for example here, right, so this for jump. And then you need to consider this dynamic on three components. The key point is that structurally, because they kept the rates, structurally they're the same as the original dynamics. And apparently, or at least so far, all results known in this area, then you can show the existence of evolution, they're to a certain extent structural. So if the rate has certain structure, then you can show something. If the structure is a bit different, you cannot show, you need another method. So because of this informal answer, if you can do this in spatial case, you can do this in spatial temporal. Let's put it this way.
Are there any further questions? Please, I'm sorry.
Does this only work for pure jump processes, or can we let them like diffuse or move around like Hamiltonian flow?
Yeah, natural question, of course. Yeah, my understanding is that if you take 2 moments of time and you allow diffusion, that at this moment of time, almost all particles move. They change their position, right? So because of this method will not work. Yeah. So what is possible to do, of course, it's possible to do different tricks. You may consider non-local diffusion, right? Like you actually jump, you may get result and then pass to the diffusive limit in the answer, right? But this, then it would be a bit delicate question, whether what you get would be relative to what you need originally, right?
Okay, so Emma, thanks again.
Thank you.